Yeah, and as people were kind of filtering in, the three organizers on this call, myself, Soon, who's helped a lot logistics and motivating this for the past couple of years, and Adam as well. I don't know, Adam, I don't know if everyone can see you, but maybe say something and introduce yourself.
Hi, everyone. I'm Adam. I'm a third year comp bio student in the UCSF lab with Matt.
Hi, everyone. My name is Sun. I work with the Center for Computational Biology, and I'm really thankful to Matt and Adam for helping to coordinate this. And I'm so glad that we can launch this in spite of the circumstance. And thanks, everyone, for your interest in participating in this. And, you know, we put this on every semester. Also, when we did it in person, it was, we received funding from the Student Technology Fund to put this on, and we could feed you in person, but unfortunately that's not the case now. But we're so glad you can still be here with us. And as Matt mentioned, this will be recorded, so we'll send out the link to the recording after this. And also lastly, if there are topics that you would like to see for future workshops, please let us know, because we'd love to continue this next semester. And then if there's topics that are, you know, of interest to folks, we can definitely try to line up someone to present on those topics. So thanks again. And thanks again, Matt, for presenting today.
Yeah, my pleasure. Yeah, and after the talk, I'll also send out a Google poll or a form that will hopefully be useful for us in the future. So you can let us know how we did, if there's any topics we can talk about in the future, stuff like that. Yeah, and in normal years, this is really important because it lets the department know that this is actually useful to people, and it motivates funding for it. Yeah, cool. Yeah, so just maybe another 5 more minutes and then we'll get started.
Matt, also, I don't know what the protocol is. You want people to ask questions throughout the workshop, or you want to hold it at the end? So maybe let folks know, and then we can help manage the chat as well, huh?
Yeah, so I was going to say I'm comfortable with either one. I've coordinated with Adam to be my official chat reader in case I miss any questions. But yeah, for any of you who feel comfortable asking questions over Zoom, I'd love to take them, and hopefully it'll be helpful. Yeah, so do we have a website that we can find information of this seminar or seminars in general? Okay, if you're curious about this seminar, the website that we're using as the home for this is this GitHub repository, which I'll send over one more time in case that you joined after I sent it over before. We don't have a home website for the CCB skills seminar. Depending on who's given the presentation, they might come up with a GitHub repository or something else that we can use as the home. Yeah, I know that virtual talks can be kind of scary to ask questions over. So no worries if you rather use the chat box. All right, it's 10 after the hour, so let's get started. For those of you who didn't hear the introduction, my name is Matthew Jones. I'm a PhD student in the UCSF labs at UC Berkeley and the Weissman labs, formerly at UCSF, now at MIT. Not that geographical location matters in any regard nowadays, except if you live in Berkeley or the Bay Area, because apparently the apocalypse is taking place right now. So hopefully you all are surviving that comfortably, or not, at all. So today I wanted to give you guys an introduction to TensorFlow, specifically TensorFlow 2.0. These computational skills seminars, they kind of bounce around between different topics. Sometimes they can be about biology, sometimes they're not necessarily. This one is not necessarily geared towards biology, but perhaps for a skill that you might be interested in applying to your own data sets. Future seminars will talk about other things, maybe more specifically geared towards biology. But for those of you who are just joining again, I want to send over this GitHub link, which is kind of the home of the seminar today. And this is going to have just a README here, but the actual meat of the seminar is going to happen in the Colab notebook that is linked in the GitHub repository. So if you navigate to this GitHub link, you'll see I have a small introduction shown right here. And then right below the introduction, you'll see that there's a link to this Colaboratory. So I'm going to navigate to this right now. And this is going to be the tutorial as you walk through how to use TensorFlow. So hopefully I don't lose too many people doing that. And so I suggest if you have the ability to do so, to navigate to this Colab as well and follow along. So I'm going to give you a second or two to get to this Colab, and then you can make a copy of it in your own Google Drive by just saving a copy like this right here. So let me give you just 2 minutes to do that. And I'll be monitoring the chats if anyone has any trouble. So once again, you navigate to the Colab from the GitHub, you click File at the very top, save a copy in Drive. Okay. Yeah, so hopefully that went smoothly. I don't see anyone asking any questions in the chat. But just basically, if you haven't used Colab before, it's really neat. It's actually based off of Jupyter Notebook. So if you use Jupyter Notebook, it interfaces almost exactly the same. The only difference is you don't need to have an actual computer to run the stuff on. It's actually leased from Google for free to users, and they have CPUs and GPUs and memory that you can use for free, as well as an interactive notebook, essentially, which is a nice environment to develop in or lead tutorials in. And what's also really neat is that Colabs come with a default kernel that already has all the software you need for basic things like NumPy and Pandas and TensorFlow. So hopefully this will be pretty seamless to get started in. And hopefully you might even be converted to or convinced to use Colab in the future, because it's a pretty nifty tool and easy for sharing. So in this tutorial, not only do I want to sell Colab, but also I wanted to give you an idea of how to use TensorFlow 2.0. So for those of you who are not coming from a machine learning background, maybe you've never used TensorFlow, you never used another library for doing deep learning research and machine learning research. But suffice it to say that there are many options out there, and this is just one option. In the research community, PyTorch is very, very popular because it gives you a lot of flexibility of defining your fancy neural networks and loss functions. It does something called auto differentiation, which is really cool. And we're not going to get into those details too much. TensorFlow, on the other hand, though it was kind of unwieldy in the first iteration and really only popular for developers because you had to get used to like this abstract session idea. 2.0 is a lot more tractable, I think, for someone who's just getting started with machine learning research. Hopefully you'll see how easy it is to define even really sophisticated deep neural networks and run run a classification or regression or something like that. So I wanted to cover 5 main things in this tutorial. The first one is just generally speaking, to just define machine learning and kind of tell you how to identify what type of machine learning problem you might be faced with. The second one is showing you how to use a very simple linear regression to predict miles per gallon of a car. The third thing I want to talk about was just kind of like ramping up how sophisticated we can get with TensorFlow. And to do this, we're going to make a deep neural network to classify handwritten digits using the MNIST data set, which you might have heard of before. And then the last two items are going to be more about practical things: saving, loading, checkpointing models. So you can read in a model you've already trained. And then the last thing is to create these Tensorboard reports that can actually compare the performances of different models to one another with this really nice web-based user interface that bakes right into Colab, which is pretty neat. So I'm anticipating that you all will be able to follow along and that Google doesn't have a problem with 50 or so people running collabs. Typically that's not a problem. So follow along if you can. And I think it'd be more fun if we can kind of experiment with different neural network hyperparameters and architectures and let each other know what works and what doesn't work. So the first thing we want to do, of course, is import libraries. And actually, just pause right now and just ask if there's any questions about what the scope of this seminar is, or if there's any any problems that you've encountered just even getting to this page. So let me pause for 30 seconds and see if anyone pops up on the chat or wants to ask a question. Okay. All right. Perfect. Okay, so the first thing I wanted to talk about was just identifying a machine learning problem. And I guess when you talk about machine learning, you have to kind of define what it is in general. And I think that in popular culture, it really depends who you talk to about machine learning. Sometimes machine learning can be used to describe the Terminator and how the machines are going to take over the world. Sometimes it's described or it's used to refer to something as simple as predicting whether or not you'll like this movie or not. And so it's really kind of a marketing term it's become recently, especially living in close proximity to Silicon Valley. And even to muddy the waters even more, there's also artificial intelligence and statistical inference that are all kind of used either interchangeably or slightly different ways. And I think that the simplest answer I can give you, what machine learning is, and artificial intelligence for that matter too, is just pattern detection. So ultimately, when we're talking about machine learning, at least in research, is we're trying to detect patterns to either make decisions or make predictions. And importantly, there are two classes of machine learning problems, generally speaking. There are supervised machine learning problems and unsupervised machine learning problems. Supervised problems are ones that have a ground truth label that you're trying to predict, such as whether or not there's a cat or a dog inside of an image, or if you want to predict the housing prices, for instance, of several houses given the geographic location and the age of the house. So like I said, supervised requires a ground truth. Unsupervised does not have a ground truth. The ground truth in unsupervised problems are hidden from you. And so oftentimes the goal is to then infer the structure in the data. So for instance, if you've done any clustering before, for let's say gene expression matrices or DNA sequences, these are all unsupervised learning problems. And that's actually much more common in biology because ground truth labels are really expensive in biology. So oftentimes you are stuck with unsupervised problems. The next distinction is, especially with reference to supervised problems, you have regressions and you have classifications. And just to define this really quickly, regressions essentially are problems where you're trying to predict like a real value or an integer that have some ordering to them. So like the prices of something or the age of something. Whereas classification is concerned with categorical data that is unordered. So for instance, cat or dog, or in the case that we'll see later on, trying to predict the identity of a handwritten letter or a handwritten number. Yeah, so in this tutorial, we're going to stick to supervised learning problems. This is probably the easiest way to approach machine learning. And you might see later on that I refer to refer to examples and labels using symbols or variables. And I'm just going to note this really quickly. Oftentimes we say the observations are denoted by X's. And if we're talking about the ith observation, you can note that it's xi. Each observation is defined by a set of features. And oftentimes we say that there are D features. And every single example is going to have the same number of features. And then in the case of supervised problems, we also have labels, which we denote as Y sub I for the ith example. So these are paired. Okay, any questions before we jump into the first example, which is a linear regression for predicting miles per gallon? I see that there were, yeah, some people were just joining, getting up on the collab. Yeah, so any questions? Okay, cool. Okay, so one of the nice things about TensorFlow, especially TensorFlow 2.0, is it has a bunch of really nice data sets already baked in. So we're just going to use one of the data sets. So if you run this cell right here, you can see that we're able to load in this auto MPG data set. These are the columns. We're just doing a little bit of parsing to get this into a nice data frame. One of the things we do is we rename the columns to make sure that things play nicely with TensorFlow. TensorFlow doesn't like when you have spaces in names, which is for computer scientists, this is like already kind of like you kind of do automatically, but perhaps isn't really obvious. Another thing is we have one column that has to do with the origin of the car, and we're going to convert that to strings to make it more clear that it's a categorical data item. So if we look at the data frame, which is nice, Colab already has like this Pandas Viewer inside of it. You can see just the first 5 columns, you can see what the structure of this data frame is like. So I've already said this a couple times, but we're going to be predicting the miles per gallon of a car. And then these are if this is the label for a supervised learning problem, we're going to have a set of features as well that define, that hopefully we can use to learn the model for predicting MPG. So we can see that you have cylinders per car, you have the horsepower per car, acceleration, the year that the car was made, and the origin. And so this data frame, what's nice about Pandas is it can mix different data types. This is something that NumPy can't do, which makes interfacing with linear algebra a little more difficult, but for the human eye, it's easier to look at. Nice thing about TensorFlow is it has a lot of capabilities for digesting categorical numerical data. But you can see that, for instance, cylinders is numerical and origin is categorical. So basically, you can't say that USA is greater than Japan necessarily, but you can say that 7 is greater than 8. So that's the difference between numerical and categorical data. So we've read this data in. Now we want to frame the problem and prepare the data for training. So the problem statement, essentially, is a question. And so right now we're concerned with what is the MPG given the number of cylinders in the car, the displacement, horsepower, et cetera. But you can also imagine taking any one of these columns and asking the same question, just kind of slightly reorganized. You can ask, what is the model year given the number of cylinders, so on and so forth. So really framing the problem is just coming up with a question and being able to translate that into a learning task. Like I said, we're going to be concerned with learning the MPG. So once we frame the problem, we then want to prepare the data. Oftentimes, we want to do some data sanitization. So we can see that a couple of entries in our data frame have missing values. This is a nice Pandas intrinsic function that is going to check inside of the data frame if there's any missing data. And so we can see we do have some missing data. We can drop these from our data frame just with this drop in a function. And then after you kind of like just done this data sanitization, you want to look at the relationship between your label and the other features to see if there's any outliers or if there's any need to do any crazy other data sanitization. So Seaborn has this really nice function called pair plot in it. And pair plot will allow you to look at the dependency between your Y variables, in this case MPG, and a set of other variables in your data frame. And just generally speaking, you can actually do like a big diagonal plot where you can look at the relationship between every pair of variables, but we're really only concerned with how MPG is related to the other features. So you can see that generally speaking, there seems to be a lot of dependency between some of our features and miles per gallon. For instance, displacement has a negative correlation, horsepower and weight have a negative correlation. Weight kind of makes sense. The heavier the car, the more gas you're going to need essentially to get where you're going. Model year is positively associated. It makes sense. As time has gone on, you have gotten more efficient. And you can see that for these numerical data set, numerical features, you can actually make claims about positive and negative correlation. But importantly, the reason why we like to separate categorical from numerical data is that if you look at categorical data, it's unfair to say that there's a linear relationship between our label NPG and these categorical items. Instead, you can make claims about Japanese cars have higher NPG on average than USA, but really any linear relationship is a function of how you're plotting the x-axis. Anyways, that's just a subtle point to make. But looking at this, it doesn't really seem like there's any crazy outliers. We don't need to do any real data sanitization. That's kind of expected. This is a default data set that TensorFlow produces for you. And this isn't going to be any data set that you just pulled off the sequencer, for instance. So it's highly recommended that you inspect your data and make sure that things look reasonable before moving to the machine learning task. Okay. So as I mentioned before, we have this categorical data type that we don't necessarily want to feed straight into a model. The TensorFlow does have ways for doing this. It's not really worth getting into. It's a little more complicated. So what we're going to do is we're going to create dummy columns for the categorical data. And so dummy columns here refer to one-hot encodings. So what we're going to do is for the origin column, we're going to split this up into 3 columns. And if an item has a 1 in the first column, it'll be USA. If it has a 1 in the second column, it'll be Japanese. And the third column, it'll be European. And so that's essentially how we're going to convert the categorical data into numerical data. I see there's a question. Do any of the ML algorithms handle missing data, or do we always need to remove missing data manually before using ML? So it's typically recommended that you either impute missing data or remove missing data altogether. Though TensorFlow does have a way of specifying what's a missing data item, and it'll handle this for you automatically. But typically, what you can do is you can set missing data to be in the categorical or in the numerical sense. You can set it to be the mean of the feature, or if it's in a categorical column, you can set it to be the median as well. So there's ways of imputing this, or you can just drop them. In this case, we're just dropping them. Does that make sense? Yeah, okay. So basically, after we create this set of dummy columns, we're then going to split into train and test. And this is a common technique in machine learning. So you can build a model off the train set and then test on a held out data set, subset of the data set.
Hey, Matt, there's actually one more question about the one-hot encoding, I think.
Oh, yeah. Okay, perfect. Can you explain again the value of assigning a numerical value to categorical data? Yeah, so why don't we just take a look at this right here. So if we look at train data frame, we notice that we don't have origin as a column here anymore. We have Europe, Japan, and USA instead. So what we did is we took the column origin, which is categorical. You can't say that USA is greater than Japan necessarily. They're different categories. And we've expanded out that column into 3 columns. Each column is a one-hot encoding. One-hot meaning it's a 1 if that value is present in that row. It's a 0 if it wasn't. So what you can see is that example 146, what used to be there was origin was USA. So now there's a 1 in USA, a 0 in Japan, and 0 in Europe. Does that make more sense? That's a good question. Yeah, this is a common technique. Okay, so now we're kind of ready to train data. So we're going to take advantage of this feature column idea in TensorFlow. So this is one of the things you don't need it, but I thought it was worth talking about because it's a common thing you'll see in examples And you actually might find it useful if you don't want to do the one-hot encoding. There are feature columns for handling categorical data. And this feature column is essentially an interface for telling the model how to handle that column. So what you can see is that we're going to define the columns that we're going to use as training examples: cylinders, displacement, all the columns in our Pandas data frame. And then we're going to iterate through each one of these numeric features. We're going to want to normalize our data. That's common practice. So we'll just do that as we're going through. And then importantly, we're going to create a TensorFlow feature column, numeric column, that's going to tell TensorFlow how to operate on this feature. So you can see that I'm iterating through feature names. I'm only giving the feature column the feature name. I'm not giving it any data. And all this is going to do is just going to tell TensorFlow, when you see a column or a data type labeled with this feature name, I want you to treat it as a numeric column. There's other columns, feature columns, like I said, for categorical data. And it's the same idea. You're just going to tell TensorFlow how to handle that column when it sees it. So we're going to run through this. You can see I've created a numeric column for each one of our Pandas columns. So you can see we have a numeric column for cylinders, displacement, horsepower, so on and so forth. And there's a small disclaimer here saying you don't always need this. As I'm going to show you later on, you can, if your data is already all numerical, you can just feed it into a TensorFlow neural network. But like I said, I just want to give you an idea of how this works here. Another thing that's worth mentioning is that TensorFlow has its own dataset object, which is a wrapper around things like NumPy or Pandas data frames. And these are nice because it allows you to automatically batch and shuffle your data. So it's kind of like this wrapper that has like these methods that'll help you do this. So we're going to declare this function, data frame dataset, which is a helper, so you don't need to worry about doing it. You can just call data frame dataset on a data frame and let it know what column is you're going to use for the label. And we're going to convert both our training and test data frames into data sets, TensorFlow data sets. And now we're pretty much ready to train our linear regression. So we're going to create the model with 3 different steps. The first one is we're going to define what the model looks like. And this is essentially defining what the graph will look like. So in linear regression, this graph is literally just a feature layer. So the features, cylinders, horsepower, et cetera, fed into a single output node. And that is just going to be a linear combination. And then what we're going to do is we're going to compile this graph with an optimizer, a loss function, and other hyperparameters that will be needed for training. And then every single iteration, we're going to feed data into the graph. It's going to output the linear combination, and it's going to compare it to the label. You can compute a loss using the loss function you specify while compiling. And then it's going to optimize by feeding back that loss and readjusting your weights to train the model over epochs. Yeah, and so that's what training is essentially, is just that many, many times. So I created a helper function that you can use to create and compile a regression model. As I said before, what we're going to do is we're going to instantiate a model. We're going to use the Sequential API. Let's not get too much into what Sequential API means right here, but I think it'll be clear if you follow along here how we construct this. This is just basically an empty graph. We're going to add a feature layer like this. So this is what I was talking about before. We're going to add the feature layer to the model and a single output layer right here. There's no activation function. So it's just going to be literally a linear combination that we just return through in, that's what a linear regression is. We're going to compile, as I said, with an optimizer and a loss, and then metrics we want to trace. So in this case, just the mean squared error. This is going to return the model that we just created. And then we can define a train function as well. It's just kind of a helper function. That's essentially just going to call model.fit, but it's also going to shuffle and batch our data, as well as train over epochs and produce an output. Yeah.
Can you talk a little bit more about like the optimization and like what an epoch is, learning rate, et cetera?
Yes, absolutely. So basically, the way we train these trained neural networks is we feed data through, and we can compute an error by comparing the predicted output and the ground truth label. And so we can take this error, and then depending on how we specify the optimizer with the learning rates, we're going to learn from it. So basically, the way the neural network is going to work is we're going to feed through data, compute an error, and then we're going to propagate the errors back and readjust our weights in a process called backpropagation. And how much we learn from the weights is controlled by this learning rate parameter. So if you have, so essentially if you have 10 errors that you want to propagate back, you can weight how much error you want to actually propagate back with this learning rate. This learning rate is typically between 10 to the -2 and 10 to the -6 maybe or so. Epoch is how many times you feed the data through altogether. So when you feed, let's say you want to feed the whole entire data set through the neural network 10 times, that'd be 10 epochs. And batch size is how many examples you want to feed through and aggregate the error for at a time. So essentially, this is how it would work. You would batch your data into, let's say, batch size of 128 examples. You're going to feed those 128 examples through your neural network. At that point, you're going to aggregate the loss, propagate things back depending on the learning rate, and you'll do that process until you finish the entire data set. And then that is one epoch, and then you'll keep going for how many epochs you'd like. Is that a clear example or a clear description of these different parameters?
Maybe, do you just want to touch upon gradient descent, like briefly?
Yeah, so gradient descent, if you imagine you have this loss function, it's oftentimes convex if it's a mean squared error, meaning it looks like a parabola like this. The idea is that if you can compute the error at any one of these positions, you can compute in which direction the weights should be shifted in order to get the error down to the bottom of the parabola. And you want to essentially get to the very, very minimum of this parabola, and that's essentially your optimization problem. Yeah. So I'll send out, I mean, if you're curious about how machine learning works in this sense, probably you're better off reading an actual tutorial on all these algorithms. Yeah. So hopefully that kind of answers essentially what the optimizer is doing. We have another question. What's the difference between batch size and learning rate? Batch size and learning rate are going to scale almost negatively with one another. So if you have a really high learning rate, you can probably get away. Well, if you have a really high learning rate, you're going to take into account the loss a lot more. But if you have a very high batch size, you're not going to learn fast enough, essentially. So you want to have a low learning. If you want to have a high batch size, you probably want to have a low learning rate. Another way around. Yeah.
I just want to add quickly, if people are interested in this, there's CS281A, which is like machine learning for non-CS grad students, and you go really in depth with like stochastic gradient descent and all these things.
Yeah, it's better suited for an actual course. But yeah, okay. So this is linear regression. We also have this loss function we're going to plot. Okay, so let's see how this looks. So I'm going to specify batch size. We're going to use a batch size of 8. So we're going to use 8 examples to learn on. 100 epochs and a learning rate of 1 to the -2. And we're going to take advantage of this helper function I wrote, which just feeds to the feature columns, the learning rate, and then we're going to train on that model that it creates. So you can see that when you do this, it's going to iterate through several epochs. Each one of these epochs is a full round of feeding the data through. And you can see how the loss tracks the mean squared error and the loss, essentially. And we can plot what this looks like. So basically, this is often what you want to do after training on a data set. You want to make sure that you reach a convergence of the mean squared error, whatever loss you're looking at. So every single epoch, like I said, is one pass to the data. And the first time you pass the data through, you're pretty much at random instantiation. Like you haven't learned anything. But over time, you'll see that this loss curve decreases. And maybe at around 50 or so, we have kind of converged. Now, we also plot the train mean squared error and the validation. In this case, it's the test because we only have 300 or so examples, so we're using the test of the validation data set. you can see that actually these, the validation data set is not used to train on and not used to compute the error. We can just, at every single epoch, just evaluate how well we can generalize. And so you can see that these things more or less agree. So in this small example, we're probably not overfitting too much, and we've learned pretty well. Any questions, or were people able to run that code right there? So I see there's another question. How do you decide what the batch size and learning rate is to use for training? There's not really any good rule of thumb at first, as far as I know, and except for a reasonable learning rate, we're probably to 1e to the -4. Good to start. I've kind of played around with this enough where I know that 1e to the -2 is probably a good learning rate. And then batch size, you maybe want to play around with powers of 2. So 8, 16, 32, so on and so forth. And this is such a small data set that you probably don't want to use like a batch size of 256, because that's pretty much the entire training data set. Yeah. Okay, I assume that that worked for everybody. Okay, cool. So with the linear regression out of the way, hopefully that made sense how we made a linear regression model. We're gonna get a little more sophisticated and specify more sophisticated neural network architectures. And for this task, we are going to use the MNIST data set, which is a data set of handwritten numbers that the post office put out, I believe. That's essentially the goal was to do automatic labeling of addresses. And so they wanted to come up with a machine learning algorithm or model for predicting what the address was from handwritten labels. And I see that there's 2 more questions. I'm just going to answer really quick. Why is having a batch size equal to the entire data set size bad? Well, you're just not learning as much every epoch, essentially. So if you're using a batch size of 1, that means you're going to learn every single training example. But sometimes that is both computationally not as efficient, and also maybe you don't learn enough with a single training example. Maybe you want to batch together a subset of the data set. The other thing that should be considered is that if you have a really large data set, sometimes you can't fit the entire data set into memory. And so training on the entire data set as a single batch probably just won't work due to your RAM constraints. So both for training efficiency, training capabilities, but also memory, that's probably smart to use a batch size that is not the entire data set. People are also curious about, is there a way to set batch size in relation to the size of your training in our test data? Yeah, so you might want to pick an order of magnitude lower than your test data set, or yeah, just or not test data set, your entire data set. So something around like, if you have 10,000 examples, maybe you want to use 128 or something like that as your batch size. Are any glaring signs to look out for when your learning rate or batch size are wrong? Yes. So if your learning rate is too high, what you might see in this loss curve is that there's a lot of instability as you come down. And that means that you're learning too much essentially every time, and the model is making a mistake. And that parabola of loss curves, you're jumping back and forth between, you're skipping over the optimum at the very bottom, essentially because the gradient is too large that you're moving in every single time. The other thing is, if you don't see this convergence, it's likely that you haven't trained long enough, or your batch size is wrong, perhaps, because you're not learning enough, essentially. So if we'd only gone for 20 epochs, you would see that this curve had not converged, and this is a problem. So you either want to train for longer or decrease your batch size. Yeah, and if it's too low, your convergence will be very slow. Exactly. Okay. Perfect. Any glaring signs to look at? Yeah, I think I answered all this. Perfect. Okay, so for this more sophisticated neural network, what we're going to do is not only increase the depth and the number of layers in your neural network, I'm also going to introduce this concept of regularization, which is very common in machine learning. So one of the problems that we didn't see above, but is very common, is that you cannot generalize your model to held out data. And this is a problem called overfitting. One of the really common examples that I've heard is that I think it was the US Department of Defense was trying to predict whether or not an image had a tank inside of it or not. and they didn't have a good test data set to detect this on. So in their training, they're like, oh, this is fantastic. We have model performance like 100%. But when they tried to put out to test data set, their model performance tanked. And it turns out that all their training data sets were during the day, and the model was just learning whether or not it was day or night. And so when they tried to generalize to a test data set, this rule didn't hold anymore and the model performance tanked. So you want to make sure that you are able to generalize. And one of the ways to do this is to regularize. And there's two common ways of doing this in machine learning for deep learning in particular. One of the ways is using hidden layer dropout. So after every single layer of the neural network, you can drop out a specific proportion of nodes. So the model can't just get used to those nodes and can't use just one feature or set of features to make a prediction. It's forced to learn a lot more, and it can be more robust that way. The second way is using something called weight decay, which is the same thing as L2 normalization. And if you've taken a machine learning course, you've probably heard of ridge regression, which essentially penalizes the amount of weight that you can use. So essentially, you essentially want to penalize essentially the case where if you have two features that are capturing the same amount of information or the same information period, you're not going to assign them both the same weight. You're going to split the total weight between the two. So it's forcing the model to spread out how much it can learn. And this is what ridge regression looks like, and you just can apply this same idea to neural networks. So, and the lambda is the parameter that you're specifying. That's your hyperparameter. So if you specify a lambda of 0, there's no ridge regression. You're not penalizing the amount of weight they're using. And if lambda is 1, that's a lot of ridge regression. A common amount is between 10 to the minus 3 and 10 to the minus 6, maybe. Okay, so hopefully this regularization made sense, and hopefully made sense what we're going to do. We're going to predict numbers between 0 and 9. And this is, I just want to be clear that this is, these are handwritten digits. We're not comparing, it's not a regression, it's a classification. So we're going to read in the data. And I wanted to show you what this looks like. So you can see that these numbers literally are just bitmaps. So 0 if there's not handwritten anything there, and a 1 if it is. So you can see that this is a 3, and you can play around. You can see what the 888th example looks like. We're going to specify a new model. This looks very similar to what it looks like before. The only difference is that we're not going to have a feature layer. We know that all of our data is numerical already. We're just going to tell it how many items to expect in the feature, or in that first input layer. And since we know that MNIST data sets come in a 28 by 28 grid, we can just flatten it so it can be 784 elements to expect. And this function does that for you. We're going to tell the neural network how many layers we want and how many nodes per layer. So we're going to iterate through, for layer and n layers, we're going to add a new layer with the L2 normalization that we specified. So it's the same format as we used before in linear regression. We're going to create a new dense layer, but now instead of a 1 neuron, we're going to have the number of neurons that we want it to have. An activation function, typically this can be ReLU, or you can have a tanh activation function. ReLU is probably the most popular. And then we're going to feed it the weight decay normalization that I just talked about before. We can also add a dropout if we'd like, the hidden layer dropout. And then finally, the output is not going to be just an identity output like the regression before. Right now, we're making a multi-class prediction. And so this output is going to be a softmax activation. And what it's going to do is it's going to produce a probability at every single one of these classes, which we can then use to predict. We're going to use the same optimizer as before. There's no reason to change the optimizer for this classification task, because it's just simply a gradient descent problem still. We are going to change the loss to be a cross entropy, which is typically used for categorical data prediction. And we're also going to track accuracy, not the mean squared error. The trained function looks almost identical. So you can see right here, I'm going to specify some model hyperparameters, the number of layers I want to use, the number of neurons I want to use, the dropout, weight decay, as well as some training hyperparameters, the learning rate optimizer, the number of epochs to train for, the batch size, and the split size. validation split size. So how many data points to hold out at every single epoch to make sure we can generalize. And so let's run this. Let's see, I'm going to run for 50 epochs. And maybe you all are running it as well. Maybe you felt adventurous and wanted to change some of these hyperparameters. And yeah, so I'll answer that question as this is training. So what exactly is a layer? A layer is essentially a linear combination of some sorts. But after the linear combination, you apply the activation function. So essentially, the way these neural networks are formatted is that you have a feature layer, which is just your input. So before, in the linear regression, it was like the cylinders, the acceleration, so on and so forth. Now it's going to be every single pixel in our image. And then we're going to feed it through a bunch of layers. And this is the idea behind a neural network, is that you have many, many layers, and each layer talks to the nodes in the subsequent layer. And after every single layer, once we're done, we can then feed it through an output layer, in this case, a softmax output layer, to make predictions. Hope that was clear enough. So we can look, after we trained the model, that we can look at the loss function again. In this case, we're just looking at the accuracy as a proxy for the loss. And you can see that both train and validation seem to meet up at about this 15 epoch mark right here. And we actually get pretty good accuracy, about 97% accuracy. One of the things that I've noticed before is in TensorFlow, at least when you're specifying validation data as well, is that the validation accuracy can sometimes be a lot higher than the training accuracy. And I think this is because of the way their fit function works. I think it's after it's learned, it compares to the validation. It compares to the validation data set. So oftentimes you're essentially comparing the training accuracy before, and then before you update your weights, and then validation after you update your weights. So that's why there's this kind of discrepancy. Okay. So just in the interest of time, maybe we'll continue on to saving, loading, and look at Tensorboard as well. But you can use this notebook to play around with and see if you can find better parameters to get better accuracy. So one of the things that you might want to do is after you train a neural network, you want to save it. So you don't need to retrain and make predictions. You can just load in the neural network and make the predictions that you've already learned. Not everything's like MNIST or that's MPG examples. Neural networks typically take a really long time to train. You might have many, many different experiments going on. So it's not really feasible to do everything over again every single time you want to make a prediction. So what I want to show you here is how you can save and load neural networks. And the first way to look at this is to show you how you can re-parameterize a new blank neural network with the learned loadings from the previous neural network. So what we're going to take is this MNIST model that we just trained. We're going to get its architecture. So when you get a blank neural network model, you can just take the same architecture that you've already made and just load it in. We're also going to get the weights for every single edge in this neural network. And we're going to specify this new model, which is just going to take the architecture from the JSON that we just created up here. We're going to set the weights with the MNIST model weights that we learned previously. And then we're going to use this new model to predict on the test data set and then look at the accuracy. So if we do this, we can see that even though we made a new model from scratch, we're getting accuracy that's extremely good, meaning that we got really lucky, or this is effectively loading in previously learned neural networks. So with this in hand, what I wanted to show you is how you can actually checkpoint models while you're training. It's not always the case that your final model after training is your best model. Sometimes model performance tanks towards the end of a training run, or maybe it starts to overfit, and so the validation accuracy plummets. And so what you can do is you can checkpoint while training with TensorFlow to save the best model along the way. And the way we do this is with a callback. So callbacks are functions that you can feed to model.fit that after every single epoch will produce some functionality, in this case, saving the best model thus far. So we're going to define a new train function, which looks very similar to the train function before. The only difference is now we're going to specify this checkpoint, which is going to monitor the validation loss and save the model that has the best validation loss. That makes sense? And at the end, we're going to return the model architecture, not the model itself, and the history in case you want to plot something and see if this reproduced something that you thought was reasonable. Okay, so let's make this function, and then we're going to train now with this checkpointing function. I'm just going to do it for 10 epochs. Okay, and then you can look that in this directory that Google Colabs give you for free, temporary directory, you'll see that we have a new file in here called model checkpoint. And you don't need to worry about what's in these files. You can just know that you can read those weights in. So with this model.loadWeights function, it'll read in these files from temporary. So once again, we're going to take the model architecture and start a new blank model called checkpoint model, load the weights in, and then we're going to use the checkpoint model to make the predictions as before. And you can see that our accuracy is quite good still, 0.96. So meaning we're able to read in the checkpoint model. This is really useful for your actual training. You can save the model and load it back in. Okay, the last thing I want to show you is this another really nifty thing called Tensorboard, which is a web-based UI for tracking the model performance over time. And so once again, we're going to create a new train model function. We're going to use a callback, but instead of checkpoint callback, we're going to use a Tensorboard callback. And this tells Tensorboard where to look for logging information. So after every single epoch, we're going to log the losses and the accuracies to this log directory, and then Tensorboard is going to know where to look, and it's going to populate a web-based report to do that, that you can then look at. So I'm going to create this new function, and then I'm going to, I actually want to do 512 batch size. So we're going to train this new function just for another 10 epochs. And then we're going to use this Colab magic to launch a Tensorboard looking in temporary logs, which is where we wrote everything. And now you have this cool Tensorboard thing that pops up right into your Google Colab. It's interactive, so you can look at different models that I've been training recently, and you can hover over and look at the loss as a function of the epoch. You can select specific models you want to look at. You can only look at validation. You can search for models like that. So it's really cool, I think. And if you've trained a bunch of models, you can look at how they all did comparing to one another. And yeah, this model right here, 2020, 910, 15, 2248, seems to have the best model performance. So then you can go in, read that in from a checkpoint, and make your predictions. Yeah. Okay, so that's pretty much all I wanted to talk about today. If you go back to the GitHub site, there's some other resources you might be interested in. Tensorflow has these really nice estimator classes that are kind of like plug and play. They require a little bit more knowledge about the ecosystem that I didn't have time to get into. But if you feel motivated, you can learn how to use boosted trees, classifiers, or regressions. With TensorFlow, they have their own linear regression class that you can just plug in and play. You don't need to find the graph structure. Yeah, so I encourage you to look at that. There's some other tutorials that I linked there, as well as this other tool that's very similar to Tensorboard that's called Weights and Biases. And that is a fantastic alternative to Tensorboard and has some other functionality that you might find interesting. Yeah, so that's everything I wanted to talk about. I hope that was helpful. There are more questions that I anticipated, which is great. I wanted to give you some more time to play around with this collab. So unfortunately, we didn't have time for you all to experiment with it, but hopefully you did that anyways. I'm happy to take any questions. I'm also going to attach a Google poll right here. Hopefully that's hopefully that works right there. And if you could just answer if this was effective or not, if there's anything we can be doing to make this more effective, or if there's any other topics they'd be interested in. I know this is virtual, it's kind of tough to learn over, but I hope it was still, a useful use of your time. So yeah, I'll stay on for another 10 minutes or so. You guys can all feel free to just bounce if you want to, or you can ask questions. So thanks so much. I see there's a question about the benefit of Tensorboard features. Can you be a little more specific? Like you're curious what's the benefit of this right here? Yeah, so basically this plots exactly what I was plotting before, but I think this is kind of nice because you can keep track of many different models. So if you had like 50 different models, all with different parameters, you can easily check which ones to plot and which ones not to plot. If you do like this hyperparameter search, you're gonna have a lot of models that do really poorly. And so you don't maybe wanna look at those. And it's just easier than matplotlib plotting all these, I think. The other things that you probably are interested in looking at is there's a computation graph you can look at, which tells you what the graph looks like for every single one of your models. There's some other things having to do with distributions of your weights after each layer, or stuff like that, which is kind of cool. I don't know if I have any of them loading in. It might be struggling to load in because my computer's working hard. But yeah, there's a lot of really cool functionality, which is pretty neat, pretty neat, I feel like. But by all means, if you feel really comfortable with matplotlib, go ahead. Is semantic segmentation a regression problem, a classification problem, or its own separate thing? I'm not exactly familiar with semantic segmentation. Maybe you can give me more the background, what the actual learning task is. Is this splitting up? Is this?
I think it's like when you like tag each pixel with like, is it a person, a dog, or like you're breaking up the image. Mm-hmm. Yeah.
It's more of a classification problem, I believe.
So you have like a ground truth data set that you're then breaking up the image into relative components?
Yeah, it was my question, and I'm working on like identifying the outline of a fossil specimen automatically. So I basically just need to like output a binary image. So, but I'm not trying to like identify it. I'm just trying to extract an outline.
That almost sounds like an unsupervised problem, actually. Being able to just do boundary detection. Correct me if I'm wrong, people who've done maybe more problems like this, but it sounds like it's almost a clustering or like a clustering problem in that sense. Does that sound right?
Well, I kind of have a ground truth because I have outlined some myself, and like I have those coordinates. So I can like for my training data, I do have like a ground truth data set. But it is also kind of a clustering problem, which is why I asked the question. It's weird.
No, that's a really cool problem. Yeah, so then it sounds like if you have this ground truth data set of things that you're trying to teach the model, it might be better looked at like a classification problem, whether or not a pixel is part of a boundary or not.
Okay, thanks.
Yeah, no problem. Cool question. I haven't heard about that, really. Okay, perfect. There's another question about the difference between model and model architecture. So you can have, let's say when you do one of like the create model functions, what you're doing is you're defining how you want the data to pass through, but it's a random instantiation of the model weights. So if you just pass data through and don't try and learn anything from it, you're just going to get random performance. But if you take the model weights and put it onto the model architecture, now you have something that actually resembles a model, how you think the label should be predicted given the input data. So I guess you can say that the model, if you instantiate a model with just the model architecture, it's still a model, just not a great model. But if you put the weights onto the model, then you have, onto the model architecture rather, then you have a better model. So you could probably use these interchangeably if you feel comfortable enough. I like to think about it as architecture and weights separately. Someone else had a question about protein sequence and function data. Would you just need to add in padding and truncations in addition to hot encoding and follow a similar workflow, or does it require more sophisticated models? So is your input protein sequence and you're trying to predict the functionality of that protein?
Yeah.
Yeah, so this is a really cool problem. And it's kind of like the holy grail of computational biology, deep learning, in my opinion, is just like sequence to function. There's a lot of things you can do. So you could create one-hot encodings of each position. So now each position would be 20 dimensions, essentially, depending on which amino acid, right? So that's one way to do it. And then you can flatten that and feed it through and try and predict. Or you can use convolutional neural networks to do this as well, which kind of like don't require like the flattening aspect like we saw for MNIST. You can kind of like treat the 20-dimensional by n vector as like an image kind of, and then convolve over that, which is something I didn't really talk about. But there's a lot of, I mean, it's to the best of my knowledge, there are people who have tried to apply the convolutional network stuff to protein function prediction. Yeah, but I mean, if you have data you can play around with, try doing the one-hot encoding, flatten it like we did for MNIST. So you just take the 20 by n image, now you flatten it, and then try passing it through and see if you can predict something. See how well you do. Cool. Yeah, any other questions to answer? Okay, I'm sensing that there aren't too many other questions that are going to come through. My email address is mattjones@edu. Send me an email if you have any questions or if you want, if you have any suggestions. But of course, there's also that Google poll that I sent over. If you have any suggestions about future seminars or what I could have done better, that'd be hugely appreciated. Yeah. So yeah. I think that there's no more questions. Thank you so much for all attending and for the great participation. And hope you guys all try to have a nice week despite the chaos. And the next seminar is in October. It's the first Thursday of October at the same time. And I believe we'll be going over an introduction to Julia, if I'm not mistaken. Yeah, so thanks again. I'll see you all later and hope to see you all in person sometime in the future.